Welcome to problem solving session for computational commutative algebra. I am Siddhi Balgombure from IIT Gandhinagar, and today we will discuss problems related to syllabus from week 7, that is problems related to integral extensions, Noether Normalization Lemma, Polynomial Rings, and going up theorem. So let us start with the first question. So question 1, let K be filled, then what is the rule dimension of KT? So they are asking us that what is the rule dimension of this polynomial ring KT with coefficients from K and variables from T. So remember that in the lecture, we already have seen that dimension of KT is greater than equal to dimension of K plus 1. Okay. We have already seen this in the lectures. So if we could show that, so here we have that since K is a field, then, so in general, since K is a field, so dimension of K is what? Dimension of K is 0 because only prime ideal in KT is 0 because K is a field. So dimension of K is 1, and so the chain is only containing 0 ideal. The chain of prime ideals contains only 0, that is this p0th component, and so dimension of field is a 0 that is there. So so from this equation we have this dimension of KT greater than equal to dimension of 0 plus 1, that is 1. So we in general have this dimension of KT is greater than equal to 1. So if we could show that, so we claim that dimension of KT is indeed 1. So that is our claim. So when we say dimension, it means one dimension is dimension of R is maximum of L such that we have this chain of prime ideals. Okay. So this is the dimension of any ring R. This is the definition of dimension. So we have to find the chain, and our claim is that 0 is anyway a prime ideal in KT. Okay, so we say that if, and it is greater than equal to 1, so at least one prime ideal is already there. So let non-zero P, so P be non-zero prime ideal. Okay, so since P is non-zero prime ideal, there exists a maximum ideal which contains this prime ideal P. So there exists maximal ideal M such that this P is contained in this maximal ideal M. So what we have here, we have this chain of prime ideals because maximal ideal is also a prime ideal. So we have this chain of prime ideals, and but note that KT is principal ideal domain. Okay, so this P is generated by some prime element P, and this M is generated by some element M. Okay, so note that since KT is principal ideal domain. So principal ideal domain means each ideal is generated by only one element. So this P is generated by some element small p and M is generated by some element M. And we have then this, just I'm writing it again in terms of the generators. Okay, so since this ideal P is contained in this ideal M, this implies this element P also is inside this element small p is also inside ideal generated by this M. So these imply what? That P is equal to M into some R, or R into M, doesn't matter. Where this R is some element in R, or in our case is in KT, and M is what we have here, which is generating the maximal ideal, which contains our original ideal P. So but note that P is a prime ideal in a PID. So this, and it is generated by this small p. So this, since, let me write it, since P is a prime ideal in PID and it is generated by element this small p. So therefore this element small p is a prime element in KT. Okay, so that's why when I'm writing this P as a product of two elements, this implies this either R is unit. In this case, we get that this ideal generated by small p is actually this ideal generated by M. That is, I get that P is equal to our ideal M, which is maximal. So this imply that P is maximal ideal. And if, or, so if either R is unit or M is unit. Okay, so this was if R is unit, if M is unit, this imply that this ideal M is our whole ring KT. And then this will imply that this P is a maximal ideal. Okay, because we just chose the ideal which is above this element P, and we got that it is maximal ideal. Therefore, in PID, every non-zero prime is maximal. Okay, so therefore this 0 is properly contained in P in KT is the chain of prime ideals of maximal length. Okay, so this implies that this in short also imply that in PID, uh, every non-zero prime is also a maximal ideal. Okay, so therefore dimension of this kt is 1 because the chain, so the chain, the maximal possible chain is this p1 contained in p0 contained in p1, and this one is now our dimension of a principal ideal domain. Yeah, and what I said that in principal ideal domain, every uh, non-zero prime ideal is a maximal ideal. Yeah. Oh, I So I hope it is clear. So we started with this information which we already had from the lecture, that dimension of kt is actually greater than equal to dimension of k plus 1. So it is like this, dimension of k plus 1. And since k is a field, dimension of k is 0 because only uh, prime ideal in a field is my zero ideal. And so dimension of kt is at least greater than equal to 1, and we showed that uh, the only maximal chain of maximal length possible in kt is of length 1. So that's why it becomes chain of maximal length of prime ideals, and we get that dimension of kt to be 1. And this also proves that every non-zero prime ideal in a PID is also maximal ideal. So let us move to the now next question. So we have to check that which of the following maps are finite. Okay, so before we go to the next question, I would like to show you that how to calculate this dimension in Macaulay tool. So let me share my screen. Okay. So for example, here again we were calculating the dimension of kt. So let me calculate the dimension of kt itself for Q. So let me define this thing R to be R is equal to QQT. Then the command to be given for calculating dimension of a ring in Macaulay 2 is DIM, dimension, the short form of dimension R. And it gives me dimension of R to be 1. And since we also use the fact that dimension of a field is also 0, let us see what is dimension of QQ. And it shows me 0. And even in general, dimension of some, let me just define a ring first. Comma y comma z, and we will see that dimension of this ring R is now 3. And we can also calculate dimension of quotient rings. So if I take S to be R quotient ideal, let us take this ideal x square minus y comma z square, and dimension of S is this. And we can also calculate dimension of ideals. So dimension of ideals is a chain of maximal chain of prime ideals contained in that ideal. Okay, so dimension of, let us calculate dimension of this ideal itself. Okay, so I hope this is clear. So how to calculate dimension and for rings, ideals, and here we also calculated it for field. in general, so this dimension is the command which we need to give in order to calculate the dimension of any ring, polynomial ring, or whatever object we want in Macaulay 2. So I hope this much is clear. So let me just go back to original screen. Okay, so let us move to this now next question, which we already started, that we have to check the which of the following maps are finite, and when they're so maps are finite. So first is this kx comma y, sorry, kxy to kx comma y. Second is this kx comma y quotiented by y square minus x cube contained in this ky comma x. Okay, and when I'm writing this here, these are capital x comma y, and when I'm writing it here, this is small x and y, I mean the variables. So this where small y and small x are the images of y and x in kx comma y quotiented by y square minus x cube respectively. Okay, so I hope that much is clear. Okay, and third is z half. So z half is this is our ring. Um, this is a localization of z at a multiplication set 1, 2, 2 square, 2 cube, and so on. And the inclusion map of z half to q, and that's it. So these are the three maps which are given. So when they are considering these subsets, they are actually talking about the inclusion map between these two rings. Okay, so before we go to the actually finding the when these maps are finite or not, let us first go to the definition. Okay, so let P from R to S be a ring map. We say that P is a finite map or S is finite R algebra if S is finitely generated as an R module through this map. Okay, so this S, so we have map from R to S. So S is anyway an R algebra. But when we say that this map Phi, I mean S is anyway R algebra, and we say that this map P is a finite, or this uh, ring S is a finite R algebra if this S is also a finitely generated as an R module. Okay, so finitely generated as an R module means there exists some Z1 to Zn such that S is finitely generated such that the Z1 to Zn form a generating set for S as an R module. And when I say that I mean that every element of S is finite linear combination of this Z1 to Zn with the coefficient uh, from R. So when I say coefficient from R, they actually factor through this map P to my ring S. So if I'm saying that um, S is just, I'm just making it clear. I think we also did this last time, but let me just, for example, I say that S is RS1. Let me just write S1 to Sn. Okay. And this is just a note, or S is summation AI Si, I from 1 to n, such that AI belongs to R. And when I write this, this is actually, this is summation I from 1 to n P of AI Si such that AI belongs to R. So, sorry. So S is finitely, so it means there exists S1 to Sn in S such that this happens. Okay, so when this happens, then we say that S is finitely generated as an R algebra. So these coefficients are considered from R, but they, in order to define the linear multiplication in S, we take this phi of AI to make this linear scalar multiplication to be well defined. Okay, so this is what is finite map is. So we have to now calculate this, whether these maps are finite or not. That is, we have to check whether these codomains are finitely generated algebras over these domain rings are, or not. So first is this kx comma y, sorry, not kxy to kx comma y. Okay, and just look at this. This is anyway isomorphic to this kx. Okay, when we write this xy becomes whole one variable. Okay, and it acts as a variable, so we can just look at this kxy as a kx or ky, whichever you prefer, doesn't matter. So we have, so note that since this kxy is isomorphic to this kx or ky, which is a principal ideal domain, and which we already proved in earlier case that the dimension of this kt is 1. Okay, so note that, sorry, note that since kxy is PID, since it is isomorphic to kx, dimension of kxy is equal to 1 by question 1, which we solved already. Okay, so this is what we have. But if I take this ring kx comma y, then this ring, this chain 0. So we are, so kx comma y is a PID. So it is an integral domain. So 0 is a prime ideal. Also, we know that this ideal generated by x is also a prime ideal, and which is again contained in this maximal ideal x and x comma y. Okay, so therefore dimension of this kx comma y is at least greater than 2, right? Because what is definition? I mean from the above definition, the rule dimension of ring R is what? It is supremum of all this else such that P0 there exists a of chain P0 contained in P1 contained in PL of prime ideals in R. Okay, so we in K x comma y, we at least have this chain of length 2. Okay, so note the numbering. It is P0, this is P1, and this is P2. So we have this chain of length 2, let us consider. And so this supremum, the set which over which we are taking supremum contains at least 2. So we don't care whether it has more, I mean, we can extend this chain or we can have a chain of length more than 2 or not. But at least from these two things, we can say that dimension, also this is in kxy. So dimension of this kx comma y is definitely greater than equal to 2. This much is clear from now. But we have corollary of going up theorem which says that if R contained in S is integral. Okay, so R contained in S is integral. Okay, so this is stronger condition that something being finite. Okay, and in that case they say that this dimension R is equal to dimension of S. Okay, so when we have R inside S as an integral, then dimension of R must be equal to dimension of S. And we are given, we have to check whether these maps are finite or not. Okay, so finite maps are integral anyway. So if this was finite map, then it would have been integral map. In that case, dimension of this, so if this kxy, kx comma y is finite map, this implies dimension of kxy is equal to dimension of, dimension of kxy is equal to dimension of kx comma y. But here the dimension is 1 and here the dimension is greater than equal to 2. Okay, so this, I mean, this should have happened from, if I call this theorem star, from star, but dimension of kxy we know is 1 and dimension of k x comma y we have seen that it is at least 2 because we have the length, this chain of prime ideal 0 containing x contained in x comma y. So therefore this kxy over kx, so which contradicts, therefore this is not a finite map. Okay, so I hope this much is good enough. So, and what is the definition and so on. So, and so let us see the second one, that is kx comma y contained in y square minus x cube, y by x, right? Yeah. So just a second. So we have this k x comma y quotiented by y square minus x cube isomorphic to k t square comma t cube. Okay, so we know that this ideal k x cube minus y square is actually this y, no, x mapping to t square and y mapping to t cube. sorry, kxy. Question is that whether this in k y by x is finite. Okay, we have to check. So this is our second part, that we have to check whether this kxy quotiented by y square minus x cube inside this k y by x, and this small y and small x are images of y x and y in quotient ring. So we have already seen that. Yeah, so we have seen that this kx comma y quotiented by y square minus x cube is isomorphic to this ring kt square comma t cube, right? Where this x, so we had this original map kx comma y. I mean, we did this, I think, last week or maybe before that, such that, and y goes to t cube. Okay, so we have this isomorphism. So I just look at this element, this ring here, as this kt square t cube, and when I consider this, and this is contained in kt, okay, and this ring satisfies the polynomial and polynomial this t satisfies the polynomial x square minus t square is equal to 0 in this kt square t cube. Okay, so therefore this t is integral over this kt square comma t cube. Okay, and this, so this is everything about this ring on the left hand side. And what is this ring on the right hand side when I look at it through the, I mean, in terms of this kt square and t cube? So kt square comma, I mean, then since k x comma y quotiented by y cube sorry, y square minus x cube is isomorphic to k t square comma t cube, then this ky by x, which were images of this under this quotient map, will be isomorphic to this k t cube comma t square, right? The image of y is going to t cube, image of x is going to t square, and so on, which is kt. So we are in short looking this k t square comma t cube inside this kt, and we know that this t, we saw that the element t is integral over this kt square comma t cube. Okay, so therefore this kt now becomes finite over kt square comma t cube. So any so this is what it was asked here, to check whether this map, this inclusion in k x comma y quotiented by y square minus x cube inside k y by x is finite or not. And instead of going through this quotient map and this ring y by x, we worked with this ring. So this ring, we looked at it like this, and this ring we looked at like this. Okay, so we saw that this kt is finite over kt square t cube. Okay, so now let us, the third part of this, that Z 1 by 2 inside Q. Okay, so this, again I'm writing this, the Z 1 by 2 is S inverse Z, where Z is this multiplicative set, 1, 2, 2 square, and so on. Sorry. S is this multiplicative set, 1, 2, 2 square, and so on. So we are inverting all the powers of 2. Okay. And again, we have this lemma that let R inside S be integral and S a domain, and S is a domain. So when we say S is a domain, it means S is an integral domain. Okay. Then R is a field if and only if Q is a field. Okay, so if this was if this was finite map, it would have been an integral map, and hence if so here our Q is a field, then Z1 by 2 or Z localized at multiplicative set 2, this would have also been a field, but that's not a case, right? Because Q is a field, but this Z1 by 2 is not a field. It is integral domain definitely, but it is not a field, as this element 1 by 3, sorry, this element 3 in Z, or like this, does not have multiplicative inverse. In fact, 3 is not special in this case. Any odd prime works because we are only inverting the powers of 2. So anything apart from powers of 2 are not inverted in this ring. So we actually use this lemma to get the fact. So if it was a finite map, it would have been an integral map. And in that case, since Q is a field, Z1 by 2 will also be a field through this lemma. But we saw that this Z1 by 2 is not a field because 3 is not invertible in this ring. So yes. So the only map which was finite was this map, k x comma y quotiented by y square minus x cube inside k y by x. Okay, so out of this three, out of this three, so this was not finite map, this was also not a finite map, only this was a finite map. Yeah. Let us move to next question. So question 3. Find the height of x comma y in the ring kxyz quotiented by y square minus xz isomorphic to sorry. Okay, so we have to find ideal height of this ideal x comma y in a ring kx comma y comma z quotiented by this ideal y square minus xz. So let us give name to this ring as R. Okay. So we have this not inclusion, but this surjective map from kxyz, or let us give this name S, and forget this. Let us call this R, and this as S. So such that this X going to this X bar, Y going to Y bar, Z going to Z bar, or we can just write them as small x, small y, and small z, and without bar, doesn't matter. So if we have some P in spec S, then it is equivalent to finding P in spec R with y square minus xz contained in P. So we know how the prime ideals in quotient ring or ideals in quotient ring in general look like compared to the ring with respect to which we are taking the quotient. So for example, here the S is the quotient of R xyz by ideal y square minus xz. So the ideals in R containing y square minus xz are in one-to-one correspondence with the ideals in ring S. Okay, so we will be doing that. So note that S is a domain as this y square minus xz is prime ideal, or I can say this element y square minus xz is prime element. Okay. And we can also check this by Eisenstein's criteria. As we can see that x divides xz, which is prime in kxyz, but x square doesn't divide this xz. Okay, so this becomes a prime element using the Eisenstein's criteria. So in S, we have this 0 contained in x comma y. Okay, and because if I want to have some ideal which contains this y square minus xz, then we can see that this ideal x comma y actually contains this ideal. Okay, so if I want to consider, so I can take this prime ideal x comma y. Okay, because this y square minus xz is there. We can't just take ideal generated by x because again, this element is not there in that ideal generated by x. Similarly for y and similarly for z. So we have to look at the ideal which prime ideal which contains this ideal y square minus xz, and we have to find the height of this ideal xy. So we have 0 contained in x comma y in S. Okay, and there is no other prime ideal in between. Okay, so if there was some prime ideal containing this x comma contained in this x comma y, then it would contain, I mean, it will be either through like this way or, but that's not the case here because neither x neither or y nor y contains this ideal y square minus xz. So this is the only chain possible in our ring S. Okay, so this was my P1, this was my P2. So now let us go to what these ideals correspond to in ring R. Okay, so in ring R, this 0 is again prime ideal because we are in integral domain. And then this y square minus xz, this 0 corresponds to this y square minus xz. And this definitely contains x comma y, and this contains x comma y comma z. Okay, this ideal is contained in this ideal x comma y and z and so on. Okay, so if there exists some prime ideal. Okay, so we have to check what is height of this ideal P2 here. So we have to check whether there exists some ideal. So to check, find an ideal P such that this we have 0 contained in P contained in this x comma y. Then by going up theorem, we will also have this, right? 0 contained in y square minus xz, containing whatever this ideal correspond to here. Let us call this P dash maybe. Contained in this x comma y, contained in x comma y comma z. This will happen. Okay, but that's not true, because if that is the case, if this is the case, then dimension of this k, x, y, z will be greater than equal to 3. Will be in fact greater than equal to 4, because these we are getting P0, P1, P2, P3, P4. But we know already that dimension of, but we know that dimension of, let me write this properly. But we know that dimension of this k, x, y, z is less than equal to 3 in fact. Okay, we know that. We also just saw an example of q, q, x, y, z, and we saw that dimension of it was 3. Okay, in Macaulay too. Okay, but we got the chain of length 4, so which is contradiction. So therefore, so this was our assumption. So therefore our assumption is false, and hence height of x comma y is 1, because this is my P0, this is my P1. So height is maximal 1, because this x comma y is I just wanted to see all the prime ideals which are contained in this ring and so on. Okay, so I hope this much is clear for now. So height of this element was ideal x comma y is actually 1 in this quotient ring x comma y comma z, y square minus xz. Let us move to next question now. True or false? And they are asking whether this k x comma y contained in k x comma y comma z quotiented by xz minus y square is Noether normalization. Okay, so we have to check whether this is a finite inclusion map. In short, we have to check. So since we have to check whether this is Noether normalization, we actually have to check whether this is a finite inclusion map or not. Okay, when I have, so inclusion map, because we have this. So note this fact from the lectures that if I have this R inclusion as a finite map, Okay, so when I say this, note that, recall that it means that S is finite R module. Okay, then let this P be in spec R. So P is some prime ideal in R. Then the number of prime ideals Q in spec S, or Q in spec S, such that this Q contraction is equal to P is finite. So what they are saying is that in under this inclusion, there are only finitely many prime ideals which are lying over P in S. Okay, so we cannot have infinitely many. If you remember, we did last time question where we were trying to find the fiber, how many ideal elements are there in the fiber of a given ideal, and we got, if you remember, t minus 1 and t plus 1 as the prime ideals lying above in kt maybe of the given ideal. So it is like that. So we have this ideal P here, and we go to our codomain, the image ring, and we see, when I say image ring, the parent ring of where the image is going. So and there we see how many prime ideals are lying over this given prime ideal, and so on. So this theorem says that if I have some prime ideal in R, then there are only finitely many under finite map. The Q contraction, so the Q's in S such that Q contraction is P. This set has a finitely many elements. The finitely many Q exist in spec S such that Q contraction is a P. So that was the case. And we have to check the Noether normalization. So let us also see what is Noether normalization lemma. So theorem is Noether normalization lemma. So what we have is that if R is finitely generated K algebra, okay, and K a field, K is a field, then there exists Z1 to ZD in R algebraically independent. We can also consider them as some variables over this ring R. Okay, this independent over K such that R is finite algebra over this K Z1 to ZD. So what I have is, we have this R here, and this, so once I have K here, okay, and now I am going to this K Z1 to ZD. So this is algebra. This is finitely generated algebra, right? Because we are now, this is my polynomial ring over K in Z1 to ZD, and this Z1 to ZD are algebraically independent over my field K. Okay, inside R. And here to here, I again have this map R, and they are saying that this R is now finite algebra over this K Z1 to ZD. And when I say this finite algebra, it means it is a finitely generated this K Z1 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 Z2 ZD module. Note that this finite algebra and finite type algebra is a different thing. When we say something is a finite algebra, we mean that it is a finitely generated module. So if I am saying here in this case, let us give this a name S, for example, just for the sake of simplicity. So if I'm saying that R is a finite algebra over this S, it means that this R is finitely generated module over S. Also, R is a finitely generated S module. And when I say that this R is a finite type algebra over KZ1ZD or this S, then I'm saying that it is finitely generated as an algebra over this S. Okay, so both the things are different. Okay, please, when you try to read the questions, please understand it carefully. What are they asking? Whether they are talking about finite type algebra or finite algebra. When I say finite algebra, it is finitely generated module. When I say finite type algebra, it is finitely generated as an algebra. Both are different things. When we say something is finitely generated as a module, it is a stronger condition than when we say something is a finitely generated as an algebra. And I mean, think about this. Okay, so what we have here is, so K to R is anyway finitely generated algebra as given. So R is finitely generated algebra. But I have this ring in between such that this K Z1 to ZD is now finitely generated algebra. But when I go from this K Z1 to ZD, this is finitely generated as a module. Let me write this in the caps. Okay, this is finitely generated as a module. Okay, so it is like we have some R algebra. We have some K algebra R, which is finitely generated. Okay, so they say that we can find this algebraically independent element Z1 to ZD in R such that when I take this polynomial, I mean this algebra KZ1 to ZD, then this R is a finitely generated module over this KZ1 to ZD. Okay, so this is what the Noether normalization uh, gives us. So let us move to the main question to find whether this kx comma y kxy contained in kxyz xz minus y square is Noether normalization or not. And so we will use this fact here, which we stated, to check whether this is Noether normalization or not. So what we will do is we will start with the P in spec R. Let me give this name R here and let us call this S. Okay, so this is my R and S. So we will start with let me write again. This is my K, X, Y inclusion K, X, Y, Z quotiented by X square what is XZ minus Y square in S. Okay. So this is my inclusion map. I want to check whether this inclusion map is finite or not. And one condition which we have here is that if I have R2, R inside S as a finite map, then there are only finitely many prime ideals lying above given prime ideal of spec R. Okay, so we will start with this. So now let us work with this idea. Now let x comma y be maximal ideal in kx comma y. Okay, I'm working with this ideal now. So let m belongs to spec S. M spec S such that this m contraction is my x comma y in R. Okay, so this xy was ideal in my domain ring R. And now I'm choosing this maximal element in S such that contraction of it is my maximal element xy in R. So this M contraction extension will be now contained in x comma y. Okay, this is, oops. Okay, so this is what we have here. So we are now extending. So extension will, so equality does not hold in terms of extension. So you can check this. This implies that I want to check that this x comma y s. So I want to check all the, what I mean is that we want to, so we want to find all maximal ideals in S lying over this x comma y. Okay, so note that we have this, that k x comma yz quotiented by y square minus xz quotiented by x comma y square minus xz. Okay, xz minus y square minus xz doesn't matter. Ideal generated by them will be same. Also, we are in, I mean, we are just, also we are taking this ideal over field. So that is also the case. So that's not a problem. Or let me just write this xz minus y square, xz minus y square. And this will be isomorphic to then k xyz quotiented by this x comma y. And this is isomorphic to kz, right? Or let me write this. So this M contraction was x comma y, and M contraction extension is this ideal x comma y in S, generated by xy in S. Okay, so I want to find all the maximal ideals in S which are lying over this ideal xy in S. Okay, so this is here by second isomorphism theorem and so on, and we get this. But note that this ring now is isomorphic to this. So this kxyz is now isomorphic to this xz, and there are infinitely many maximal ideal in kz. When I say this, it also means that there are infinitely many maximal. So this is now isomorphic to this ring. It means that in kxyz quotiented by xz minus y square, in this ring there are infinitely many maximal ideal containing this ideal, if you understand what I mean. Because when I looked at this ideal x comma y quotiented by xz minus y square in this S, in S, when I want to see the maximal ideas containing this x comma y, I will just quotient it by this ring and will check how many maximal ideals are there in that quotient ring, this or new quotient ring. And because anyway that ring will have maximal ideals, which I mean, if that ring has a maximal ideal, that maximal ideal will contain this ideal x comma y. And since this quotient ring is isomorphic to kz, and kz has infinitely many maximal ideals, this quotient ring also has infinitely many ideals. It means that there are infinitely many maximal ideals containing x comma y in quotient ring kxyz mod xz minus y square. So that's why our by this the fact stated, or let me write, therefore there are infinitely, I hope this is clear. If not, please write it in the Google Classroom or maybe in the comment. So there are infinitely many maximal ideals in KZ. Therefore, there are infinitely many maximal ideals in infinitely many maximal ideals in this ring. Okay, I'm writing it explicitly: xyz quotiented by xz minus y square containing this x comma y s. Let me write this so that you will get the flavor that what exactly is happening in kxy comma s, containing. Okay, so hence by the fact stated above or stated earlier, this is not, this R to S is not finite map and hence not Noether normalization. I hope this is clear. Okay, and other way to look at this without invoking quotient or any such thing or isomorphism, we can also see that so another way that we want maximal ideals in kx comma y comma z containing x comma y. Okay, and the ideals of the form x comma y comma z minus a are infinitely many maximal ideals such that are maximal ideals such that I have this x comma y comma z minus a as maximal contains this x comma y. Or let me write this properly in S. Okay, so I hope this is uh, clear. Okay, so but this is the concrete way of looking at the things through this isomorphism and so on. So let us move to next question. Question 5. True or false? Again, so let R be a K algebra such that it is finite dimensional as a K vector space. Okay, so it is finite dimensional as a K vector space. Then K included in R. So K is R is K algebra. So we have this map from R to K. Sorry, K to R. So then they are asking whether this K included in R is Noether normalization or not. And the answer is yes, because our answer is true. Because see, we are given that K is a R algebra. Sorry, R is a K algebra. So R is K x1 to xn for some n. And it is also a finite vector space. So it is ky1 plus kyn, where each of them is cyclic modules or cyclic vector spaces. Okay, and we have this K in K x1 to xn, because this is my R in fact. Right, I can have this phi or in fact inclusion with phi of K is equal to K, and okay, so phi of K is my K, and R is finitely generated vector space and hence a module also. Module, in fact, let me write in fact vector space over K. So therefore phi is finite map, and that's what we needed, right? So this, we in short having this K to K again, and now this my R here is this K y1 to yn. So this is my, so variable, if I want to write it, it's just one. I mean, or you can take whatever element of your choice, doesn't matter. K to K x1 to xn going to R. And this is, I mean, you can, I mean, this is easy to see. So therefore, P is Noether normalization. Because from here itself, K to R, to see a Noether normalization, the system which we needed to have I mean, we already have this K to this K y1, sorry, x1 to xn, I think, yeah, K x1 to xn. So this is my finitely generated algebra, this x1 to xn. And here R to R, this K, this is my R now. This, from this R to this K y1, this is my finite map. Okay, so I hope you got that how this is happening. So the K being finitely generated algebra and finitely generated, it is finite dimensional vector space. So that's why it is happening. So answer is true in this case. It is finitely generated. Okay, so I hope this is clear. So let us move to now next question. Question 6. Let K be a field. Consider the ring map string phi from R is equal to, I'm just giving names here. Let me just write K x comma y to kt. This I will denote it by R. This I will denote it by S, with x going to t square, y going to t cube. We have to find the number of ideals in S lying over the maximal ideal x comma y in R. Okay, so we will follow the next similar step as in here. Here we again, here we had to check for the Noether normalization and we calculate the number of ideals lying above the maximal ideal in this ring. And now in this question they have explicitly asked us to calculate the number of ideals or number of maximal ideals, uh, number of prime ideals lying above this maximal ideal x comma y in R. Okay, so let us check for now. So let P be in spec case. Okay, and then or let we have this x comma y in M spec of R. So this implies this x comma y extension is this t square comma t cube contained in S. So when I write this t square comma t cube S, it means it is ideal generated by t square comma t cube in S. Okay, so in general, the image need not find ideal in S. So that's what I'm doing here. I'm taking the ideal generated by this. So this is exactly this ideal, right? Ideal generated by t square, because t square in kt, t cube belong to ideal generated by k square in kt. Okay, our S is k into t. Sorry, S is kt, where t is a variable. So that's why this t cube we can omit for now. So the prime lying over this x comma y in S are primes or prime ideals. Prime ideals. in S containing this ideal generated by T square. So, but the only prime ideal which contains T square, this ideal generated by T, right? The only prime is this single ideal generated by T. So, therefore, we get that this cardinality of primes lying over x comma y in S is 1. Okay, only one ideal is lying over x comma y in KT. Okay, I hope this is clear. We did nothing. We have been doing this throughout this lecture. But again, we just started with the given ideal, we extended it, we saw what is the ideal generated by that ideal there, and we saw all the maximal ideals or prime ideals which are lying over that uh, image ideal or extension of given ideal in the codomain. And using that, we obtained this, that there is only one prime ideal lying over this extension of x comma y, which was ideal generated by T square in S, and it was only the ideal generated by T which was lying over this ideal T square in S. Okay, so the prime lying over x comma y in S is only one. I hope this much is clear. So now next question is that which of the following ring is Artinian x comma, okay, Artinian, and they have given that x comma y are variables. Okay, the first ring is kx. Second ring is this z root 2. Third ring is kx comma y quotiented by x square comma xy. And fourth one is kx comma y quotiented by xy minus 1 comma x plus y. These are the four rings, and we have to check which of the following are Artinian rings. So let us first see the definition of Artinian rings. So, or Artinian modules. So first, to understand Artinian ring, let us first define what is Artinian module. So an R module M is Artinian if it satisfies either of the following equivalent conditions. Okay, so these are two equivalent conditions. So we say that something is an Artinian module over a ring R if it satisfies one of these properties. Descending chain condition. So when it satisfies descending chain condition on submodules of M. What does this mean? That every chain, that is every chain or M1 contained in M2 contained in some Mn of submodules of M stabilizes. When I say stabilizes, it means there exists some K such that Mk onwards, all the modules are same. It means that Mk is equal to Mk plus 1 is equal to Mk plus 2 and so on. That is Mk is equal to Mk plus J for all J greater than equal to 1. So it means that the chain stabilizes, and after a particular stage, it becomes all the modules become equal. And second condition is that every non-empty collection of submodules of M has minimal elements. So every chain stabilizes and every non-empty collection of submodule of M has minimal elements. Minimal elements with respect to inclusion. Okay, so now this was what module being Artinian means. So what is a ring? So let R be an Artinian ring. So we say that R is an Artinian ring if it is an Artinian module over itself. So ring being a module over itself means what are the submodules of a ring as a module over itself? These are specifically the ideals. So R being Artinian ring means that every descending chain of ideals in R stabilizes. So if I have a chain of ideals containing I1 contained in I2 contained in Ik and so on, then that chain stabilizes. Or uh, or and the other equivalent condition is that every non-empty collection of ideals of ring R has minimal elements. Okay, so this is what R being what I can say Artinian ring means. Okay, and apart from this, we have this another proposition proved under this definition, which is that if let R be an Artinian ring, then every prime ideal, then every prime ideal is maximal ideal. Okay, so in Artinian ring, every prime ideal is a maximal ideal. Okay, so note that there is difference. So in principal ideal domain, we saw that every non-zero prime ideal was a maximal ideal. Here, I'm saying that every prime ideal is maximal ideal. So there is a difference. Don't mix it. Okay, so let us see this. So first one is this kx. We have to check whether this is Artinian or not. So note that in kx, this 0 is prime ideal. But 0 is not maximal in kx, as this ideal generated by 0 is properly contained in this ideal x. Okay. So definitely this is not Artinian. But see, where we have these two conditions. So if it does not have any maximal ideal, sorry, this is not Artinian with using this proposition, but can we give a chain of ideals which does not terminate? So we all have seen this, that this ideal x is properly contained in ideal x square, which is properly contained in this ideal x cube, and so on. And this chain now continues. Okay, for any given power n, this x power n will always be contained in x power n plus 1. Okay, and this chain does not stabilize. So that's why this kx is not Artinian. We checked both the condition, that we got the prime ideal which is not maximal, and we also have this chain, a descending chain of ideal which does not terminate. The second was z root 2. Second one is z root 2. So this is definitely not. Second, we are checking for z root 2. Again z root 2. And is this our Artinian ring? Can we say that? No, right? Because again, this is integral domain. Z root 2 is an integral domain. So again, 0 is a prime ideal. But 0 is not maximal ideal. Because again, we can see that this 0 is contained in this ideal generated by 2. I mean, we don't even need this 2 to be maximal ideal in order to like conclude this. We just want to see, I mean, in order to say something is not a maximal ideal, we have to produce just one ideal which is bigger than the original ideal. Okay. So this is, as this 0 is properly contained in this ideal generated by 2. Therefore, it is not. And can we give a chain of ideals which is descending and does not terminate? Again, we can have this. This ideal generated by 2 is now contains this ideal generated by 4, contains ideal generated by 8, and this contains this ideal generated by 2 power n, so on. And this is proper chain which goes on decreasing and it does not terminate. Okay, so that's why this is not Artinian ring. This is not Artinian. Okay, and now the third one. So this is not Artinian. And third one is kxy quotiented by x square comma yz. Sorry, x square comma xz. So for kx comma y quotiented by x square comma xy, we have to check this. Okay, now in this case, note that this is not an integral domain. So we were using the fact that 0 is a maximal ideal here, but 0 is not, 0 is a prime ideal because we were in integral domain, but that 0 was not again giving us the prime ideal, which was a proposition which we have proved for in the lectures for Artinian rings. But now this is not an integral domain because see, x bar is non-zero here, but x bar square is 0 here in this ring kxy quotiented by x square comma y. And similarly, x bar is non-zero, y bar is non-zero, but x bar into y bar, which is xy, is 0 in this ring. So this is not an integral domain. Okay, but can you give me a prime ideal which is not a maximal here? So can we have a maximum prime ideal in this ring which is not the maximal ideal? So we can check this ring, right? This x. So ideals in this quotient ring are all the ideals which contain this x square comma xy. So definitely ideal Okay, and therefore this x bar is prime ideal in this kx comma y quotiented by x square comma xy. But this is not but this is not a maximal ideal, because again this x comma y, which is properly contained in here, is a maximal ideal in kx comma y containing x. So that's why uh, this is not Artinian. We can say that this is so using this maximal and prime ideal being maximal or not, we could say that this is not an Artinian ring. But can we again give a chain of ideals which does not terminate, or descending chain of ideal which does not stabilize? Note that if you are thinking about this y contained in y square contained in y cube, then that is not true here, because the ideals in this quotient ring are such that they contain x square comma xy. Okay, so we have to check this x comma y contained in x comma y square contained in x comma y cube and so on, contained in x comma y power n and so on. Okay, so this is chain, descending chain of ideals in this quotient ring which does not terminate. You can check that, and all these ideal contain this x square comma xy, because we have this x here. So once I have x square is there and xy is there. So all these ideals contain this x square comma xy. Okay, for all these uh, ideals which I have written here, and they are also all descending, because y square is here but y square is not, y is here but y square is not here, and so on. And you can see that, and these ideals are also non-zero here. Okay, because no x is here, so x square is there, that is okay, but xy, this, the pure powers of y are non-zero in this ring kxy quotiented by x square comma xy. So that's why these are this is the descending chain of ideals which does not terminate. Apart from this, uh, so since you saw this is exercise for you, that check for, this is not, check whether this is Artinian ring or not. Okay, check what are the maximal ideals here, what are prime ideals here, and so on. Okay, and check whether this is Artinian or not. So note that here we don't have this singleton ideal x or singleton ideal y containing in this kx comma y. Okay, so the moment I need ideal uh, prime ideal containing x square and y square, I need to have the ideal to be x comma y, and x comma y is maximal in kxy, so it will be maximal in here, and it is also a prime here, x comma y. Okay, and so and it is maximal ideal, and you can also check the chain of ideals in this ring, how it terminates and so on. Okay, so this is good exercise to understand how the Artinian rings work. Okay, now the fourth one. So again, this is not, so now the last one we have to check x comma y quotiented by xy minus 1 comma x plus y. Okay, so we have this ring kx comma y quotiented by xy minus 1 comma x plus y. Okay, so we have to find, so let's call this ring S for simplicity. Okay, so note that I have this ideal. First, let us see what this ideal is. Xy minus 1 comma x plus y. Okay, so if I multiply this by x, then yes, x into x plus y minus xy minus 1. This will give me what? X square plus xy minus xy plus 1. So this is giving me x square plus 1. So definitely this x square plus 1 comma x plus y is contained in this ideal xy minus 1 comma x plus y, right? Because xy is there and we just saw that this x, this is contained in here. Okay, now let us see whether we can have this the other way around or not, because x into y into x plus y produces this x square plus 1, and that's why this, yes, this ideal is contained in here. Now we have to check whether this xy minus 1 is contained in this x square plus 1 or not. Okay, so we have to check whether these ideals are equal, in short. Okay, so now we have this. Now we have to check the other way around, whether this, again, if I multiply this by x into x plus y, sorry. Now I have this x square plus xy, then x square plus 1 minus x into x plus y is equal to x square plus 1 minus x square minus xy. So this is 1 minus xy. And if I just take minus of this everything, I get xy minus 1. So therefore, these ideals x square plus 1 comma x plus y are actually equal to this ideal xy minus 1 comma x plus y. So therefore, and you can check this in Macaulay too. Just type these ideals and check that they are actually equal. So let me just quickly show that these ideals are actually equal. I mean, we showed this, but just to not leave any ambiguity. So let me just increase the fonts. So again, I'm in x comma y, and I have to check whether this ideal x star y minus 1 comma x plus y. So x plus y, whether this ideal is equal to ideal x square plus 1 comma x plus y or not, and it's true. Okay, and that's what we also, oh, let me just show this again to you. So this here, we check that this R is Q x comma y comma z, and here we wrote that ideal of, so this is the ideal x star y minus 1, comma ideal x plus 1, and here ideal of x square plus 1, comma x plus y in this polynomial ring R. And when I check whether they are equal here, I can see that they are actually the same ideal, that is they both are equal. Okay, so you could have just directly check it from here, but we actually proved that these two ideals are giving the same ideal in our polynomial ring. Okay, so let us now go back to what we were doing. So now, so therefore this kx comma y quotiented by, since the ideal are equal, quotiented by this x square plus 1 comma x plus y is actually isomorphic and in fact equal to this, right? Okay, and note that this ideal, this ring, if I take only this, I can look at it like, okay, so it is like coefficients are coming from kx, so it is in fact like rx quotiented by x minus a, and we know that this is isomorphic to r. Okay, or let me write it here. We know this. So I'm looking at this in this fashion, and this ring kx, y, and quotient, and this is now then isomorphic to kx, the coefficient ring. Okay, so this is what we have here. So when I do this, quotiented this x comma y, quotiented by x plus y, quotiented by this x square plus 1, quotiented by x, sorry, quotiented by x plus y. Okay, so this is isomorphic to kx quotiented by, so this is kx quotiented by x square plus 1, right? And this is nothing but, this is isomorphic to our original ring R, or let me just write it explicitly. Okay, so therefore, after this, after doing everything, this S which we have here is now isomorphic to kx quotiented by x square plus 1. So this is a quotient of an integral domain by a non-zero ideal. So we use this claim or lemma or theorem, whatever you want to call this, that if I is an non-zero ideal in PID R, let me write it explicitly, principal ideal domain R, then R mod I is Noetherian. We have this result with us. So if we prove the claim, then since kx is PID and S is isomorphic to kx mod x square plus 1, and x square plus 1 is non-zero in kx, this implies that my ring S, which is this kx comma y quotiented by xy minus 1 comma x plus y is no is Artinian. Okay, so let us look at the proof of claim. Okay, we try to prove this. So we are in PID, so every ideal is generated by some element in the ring R, and I is a non-zero ideal. So consider the descending chain. Let me write it on the next page. Proof of claim. Okay, proof of claim, that is quotient of a PID by a non-zero ideal gives us Artinian ring. Okay, so now consider the descending chain I1 quotiented by in R mod I. Okay, we have to prove that R mod I is Artinian. So we are considering the descending chain in R mod I. So this is how it will look, right? All the ideals are like this, right? Contained in some IK mod I and so on. Okay, where each of this ij contains I. Okay, that's how the ideals in R mod I are defined. And since this I and I are ideals in R, which is PID, this implies this I are generated by some AI, and this ideal I is generated by some A in R. Okay, so this AI in R and A in our original ring R. So this much is clear, I guess. So since A is contained, since this I1 is contained in I2, contained in I, K, and so on. So this Ij plus 1, sorry, AI, Aj plus 1, this ideal is contained in Aj, right? This is my Ij plus 1, this is my Ij. This is there. So this implies that this Aj I hope I have written it correctly. Plus 1 is this Aj into some Rj, right? Aj is contained in ideal generated, Aj plus 1 is contained in ideal generated by Aj. Note that here I have Ij plus 1 quotiented by, contained in Ij quotiented by I. Just to, sorry, Ij by I contained in Ij plus 1 by I. So this Ij plus 1 is contained in Ij, and so this ideal generated by Aj plus 1 is contained in ideal generated by Aj. So this Aj plus 1 is contained inside ideal generated by Aj. So it is multiple of some this element Aj, right? This is how the elements of this ideal Aj look like. Aj into R such that R belongs to I. So since this Aj plus 1 is in here, so there exists some for this Aj plus 1, Aj into Rj, right? Where this Rj in R. And also note that this ideal I is contained in I1. So I was this A, which was contained in this A1. So my A is what? Some A1 into R1, right? Where R1 in R. Okay, and so when I look at, so if this chain goes on continues, so if, and in fact this A is aj into, sorry, let me just use some also, and A is equal to some S1, where S1 is R, and general, in general, A is contained in AJ for all J. So this A is AJ into SJ for some SJ in R. So note that if when the chain descends, the if AJ plus 1 is properly contained in AJ, it means that this, sorry, AJ is properly contained in AJ plus 1. It means that this AJ plus 1 has a lesser number of irreducible factors than AJ. So if AJ is some product of k elements, then AJ plus 1 is product of, here we can see this AJ plus 1 is AJ into some other element. Okay, so this AJ plus 1 has this k plus 1 elements. At least k plus 1 irreducible contains. That's only, so if AJ has k irreducible elements, then AJ plus 1 has at least, then if AJ is properly contains AJ plus 1, then AJ plus 1 has at least k plus 1 k plus 1 irreducible elements. Okay, and note that this A is equal to AJ into SJ for all, this is true for all J's, right? So if this chain does not stop in at any point, it means that AJ, not AJ, this element A, which generates our original ideal I, has infinitely many irreducible components. Irreducible components means it is product of infinitely many irreducible elements, because every AJ kind of divides this A. And if these AJs keep on going, these AJ is properly contained in AJ plus 1 for all J's, then each that extra irreducible ideal which is getting added at every step of that proper inclusion divides this element A here. It becomes the irreducible factor of this element A. Okay, so which is not true, because we are in PID. This element A has a finite expression. I mean, this element A, then the element A will have infinitely many irreducible Let me check. Irreducible components, irreducible factors in R, which is not true, right? I mean, every element in R is finite product of irreducible elements in R. Okay. So this A being multiple of this each AJ, this A contained in each AJ kind of restrict the chain. Okay. So therefore, this chain which we started with terminates. So therefore, hence there exist some, let us say L, such that I IL quotiented by I is equal to IL plus J quotiented by I for all J greater than equal to 1. Okay. Hence, this chain of hence this chain of descending ideals stabilizes. Hence, this R mod I is Artinian ring, since we started with the any given this was arbitrary descending chain in R mod I. Okay, so if I is a non-zero ideal in a principal ideal domain R, then R mod I is a Noetherian. Okay, this non-zero is important because if I take I to be 0 in Kx, so if I take Kx and quotient it by 0, then it is again a Kx, right? And which is not Artinian, we know that. But by this theorem, we can say that the if I have a principal ideal domain and I quotient that principal ideal domain with non-zero ideal, then this R mod I is Artinian. This is Artinian. Okay, so and we use this here kxy. Kx is PID. Okay, PID is important thing because we heavily use it here, that how this ideal I1, I2, IKs are generated by single elements, and the fact that the ideal I itself was generated by a single element also played a role here, because if since I was contained in each of these AJs, we had this expression that A is A1 to AS, and each of these AJ plus 1 contains uh, extra irreducible factors than AJ when the chain descends to next step. So at each proper step, we are adding kind of a more irreducible component to the generator. And that's why we are saying, and that's make our element A to have infinitely many irreducible components, which is not true. And that's why we get here that this ideal is this ring R mod I is not it does not go on and it terminates at every stage J. Then if AJ has k irreducible component, or let me what? Suppose AJ is properly contained in AJ plus 1. If AJ has k irreducible element, or a irreducible factors, then if AJ is properly contained in AJ plus 1 and so on. I mean, I have written everything here. Okay, so this chain terminates in short, and we get that this R mod I is Artinian, where R is PID and I is non-zero ideal. So that's why. So I hope this is clear. So we started with this ring kxy comma xy minus 1, and we obtained using the isomorphism between the rings, and we also proved that these two ideals are equal, and we arrived here then that our original ring S is isomorphic to this kx comma x square plus 1. This kx is a PID, and we proved this claim result, whatever you want to call it, that if I is a non-zero ideal in principal ideal domain R, then R mod I is Artinian. And once we have this result, this kx mod x square plus 1 becomes Artinian ring, and that's why S is our Artinian ring. So that's it for today. So this is Artinian. If you have any doubt related to whatever we discussed so far, please put the doubts in the Google Classroom. And also, if there are any doubts in what we solved in this tutorial, please let us know. Also, the notes and the video recording of this video lecture will be available in the portal by today evening. So I think we can stop here. So this is what we did for today, that we find what is Artinian ring. We also checked how to find the maximal ideals lying over given ideal in the domain. We also checked that if K is finitely generated R algebra, and it is finite dimensional as a K vector space, then K over R is Noether normalization. Actually here, this being not finite also works, but we have to check here. So this actually we need to check. This need not be finitely generated. I need to check it here whether, let me write, check about the finite type algebra, check whether R is over K. Okay. If there is any, but this statement is true. If there are any errors in this, we will discuss again this next time. Apart from that, we saw the Noether normalization, how to check whether inclusion map is a Noether normalization or not. Similarly, we also calculate height of a given ideal, and we check whether the maps are finite or not. Okay, so thank you, and we will meet next week. So we are anyway above the time. So we will meet next week on Saturday again at 3 p.m. If you have any doubt, please put the questions in the Google group or the discussion forum of the course. Thank you.